So hi everyone, thanks. So this talk is a collaboration between the University of Toronto, the A-Star Institute from Singapore, and myself from Munich. And the second author, Joe Watt, is also here in the audience, so like he can maybe just say hi. And the talk is about the verification of the CVM algorithm, which I'm gonna explain what it is, and using a new verification technique for randomized algorithms, which is the actual main thing we want to present. And so basically, I'm going to start with explaining how the algorithm works. And after that, we're going to be able to summarize like what the key results of the paper are. And I'm going to also, using an example, basically explain how the functional probabilistic invariants work. And let's start with the CVM algorithm. So it was named after Chakraborty, Vinochandran, and Meel. And it's basically the initials of those authors. And the naming was actually done by Knuth. So like he made a review article and he mentioned he abbreviated the authors' last names basically to call it the CVM algorithm. So like here's the actual source of the name for this CVM algorithm. And it's a streaming algorithm. So like basically consider a long stream of elements and the algorithm makes one sequential pass of it over the stream. But the algorithm itself has like very small memory. So like it can't just memorize the entire stream. And what it does is basically approximate the count of distinct elements in the stream. So because you don't know, like you can't remember all the elements, it's actually a difficult problem because like you don't know whether when you see a new element, whether it's actually new or was already part of the stream. And to solve the problem, the algorithm uses randomization, which actually kind of is the reason for the interesting technique we discovered. And what the algorithm does, like you can't have an exact algorithm. So like the algorithm will return an approximation of the count of distinct elements with a relative error of epsilon and a failure probability of delta. So like the relative error will be within that ratio of epsilon with high probability. And basically, the lower you want to make the probability of error, the more space you're going to need. Like that's why we have this space usage. And so like if you want to increase the relative accuracy, for example, then you have to spend a little bit more space. And if you want to reduce the relative error, then you also have to spend more space. But like you can choose like for arbitrary accuracy and error probability. And the interesting part is the algorithm is quite simple and the proof is not. So it's kind of like this, those cases which are interesting. And like compared to all the previous algorithms, it doesn't use hashing. So like all the other distinct elements approximation algorithms are using hashing, and this one is actually different. It's actually very surprising that this is actually possible. And so like, just wanted to kind of use this diagram. So like when you want to think about the streaming algorithm, I always think about like a robot and it has like very small space. So like, that's why it has this pad, which is small and it can't go through the entire stream. And the algorithm is so simple that I can kind of present it in one slide. And it's basically like the state of it is composed of like one buffer. So you can see it here, right? This is the buffer and a number, which is a probability, which is initialized by 1. And as you can see, we are using a number which is fixed. The n is fixed, and it depends on the accuracy and relative error you want to have. And it's basically a limit for the size of the buffer you have. And what the algorithm does is it goes through the stream elements one by one, right, in sequence, and it makes a coin flip with the probability p. And if it's true, then it adds the element into the buffer, and otherwise it removes it. And those are like set operations. So like if it's already in the buffer, it won't change the state. And if the buffer is full, that's the interesting part. It does a subsampling operation. So it's basically independently, randomly removes every element with probability 1/2. And it adjusts the p-value. And what this does is basically the algorithm keeps track of a subsample of the stream elements and with the probability p, basically. Like, so the smaller it makes the p, the smaller subsample of the entire stream the buffer is. And that's kind of the invariant. And as you can see, like when it's finished, when it's finished, it returns basically the buffer size, like the sample size, divided by p. So it basically, because it's a subsample, you have to multiply it by the number of times you did the subsampling. That's kind of the trick. And I can also actually demonstrate how the algorithm works. So like consider the stream elements, basically like the colors are representing different stream elements, basically. And as you can see, like there are sometimes repeats in the stream. And we are going to start with p equals to 1, right? So that was the initial state, and the buffer is empty. So like, right, there is no 1 in the buffer. And so what the algorithm is going to do is make a coin flip with probability p. In this case, it will always come out heads, right? Because p is 1, so like it's basically a deterministic coin flip. And then it's going to add it, right? And then it's going to do the same thing again. And then it's going to do the same thing again. But in this case, it won't change the state because the element is already in the buffer. Oh, sorry. And so, and then when the buffer is full, now we have the interesting part. We do the subsampling. So like it will remove half of the elements. This could have been other elements. It's just an example. And then we are also reducing p by 1/2. So like from now on, the algorithm is trying to create a subsample of the stream, which contains each element with probability 1/2. So what it's going to do is, like, for the next element, it makes a coin flip. Now it's heads with probability 1/2 or tails with 1/2. In this case, it's still heads, so it will add it. So, and then it does the same thing. It makes a coin flip, and in this case, it becomes tails. So it will actually remove it from the buffer because we want to keep a sample with probability 1/2. And that's kind of like the algorithm. It's actually pretty easy. Like you can write it down in Python in like 5 minutes. And so this is kind of the summary. And okay. So I want to kind of like just mention, like, it's not the only algorithm for distinct element approximations. Like there are, for example, the algorithm by Bar Yusuf from 2001. And they also have like better properties in terms of like space usage. Or you could, for example, use them in a scenario where you can do merges. So basically you can process part of the stream on one computer and the other part, and then you can do a merge, for example. So like basically, like there are algorithms which are actually better. But like the interesting part is, like, assume you are in a situation where you can't do hashing for some reason, security-wise, or your objects don't support it, then this would really be the algorithm you want to use. Yeah, so I'm gonna summarize basically what we discovered. Or what we did. So we verified the algorithm, which is kind of obvious, right? I mean, you were expecting that. But we also discovered a more succinct proof compared to the paper proof. And it's actually based on a new technique, which is why I'm kind of like hoping I can present it. And so it could be applied to other randomized algorithms, for example. And we call it functional probabilistic invariance. That will be obvious once I explain the technique. And so like to show you like what the effect is basically like the proof with the original proof, it took like 2,600 lines, and the short version is like 1,003 lines. And you also kind of like have to remember that some of those lines are just like definition of the algorithm and so on, so like they are shared. So like this is actually underestimating the simplification. And we could, like, our proof is also more powerful in the sense that we could discover a new version of the algorithm which has better properties. And in this case, it's unbiasedness. So like basically the expected result is exactly the count of distinct elements. And we can kind of like show basically our technique is actually more flexible, and we can verify more different algorithms or variants of the algorithm. So yeah, now I basically want to kind of like explain how the technique works. And for that, we're gonna kind of call this part of the algorithm that's basically making a coin flip and deciding whether you want to add the element into the buffer or not. Step one. And the second step is basically the situation where if the buffer is full, we do the subsampling operation. And I'm gonna just ignore the last one step. And the reason for that is basically the total variational distance between the algorithm without this line removed and with is, you can compute it to be epsilon 1/2, and then you can, like, whenever you have a result which you have established for this algorithm, you can actually extrapolate it that it should be true with a correction of probability for the original algorithm. But like you couldn't actually use this algorithm because like this may overflow basically the buffer. So this is just a theoretical algorithm for now. And the last step we just call estimate. And the way to represent randomized algorithms is to using the Giri monad. So basically you have like primitive random operations, for example, the coin flips, and you just represent them as probability spaces. So in this case, we write bare P for the Bernoulli space distribution with probability P. Then you can have a return operation, and the return operation is basically just a probability space with a single element. And the interesting step is basically when you have a randomized algorithm, which depends on a parameter, which is basically composed with another randomized algorithm. So basically a sequential composition of randomized algorithms. Then you have to kind of integrate over the probability spaces. And this is the bind operation. That's kind of like the third element of the Giri monad. And that's kind of, these are the three elements you need to represent a randomized algorithm. And maybe the interesting part is like how to compute a probability of an event when it's part of a sequence. So like we have a randomized algorithm M, which outputs some value, and it's computed by the randomized algorithm F. And we want to compute like the probability of an event there. And what you would do is basically compute the integral of the probabilities for the event for each possible value F can take. and integrate them based on the probabilities of the first algorithm. So you're basically weighing the probability space based on the distribution of the first algorithm. You can also write this like as a sum here, because like usually these are just discrete spaces, so like you could just write it like that, and that's just the same thing. But we will go with the integral notation because it's like a little bit more general. And the other part is like, for example, if you want to compute the expectation of a random variable g, then you can do the same thing. You can integrate over the probabilities of the outputs of the first algorithm and then compute each of the expectation and weigh them basically based on the probabilities of the first algorithm. And so now we have the basics of the G-ring monad, and we can kind of express our algorithm using the G-ring monad. So if you recall, it's basically we are running step 1, then step 2. We are ignoring the deleted line, and we are doing it for each stream element. And then we are doing an estimation step. So like we could represent that algorithm using the G-ring monad like this. So like the first step is basically we are initializing, so P is equal to 1, and we have an empty buffer. And then we are going through the stream elements. And maybe the interesting part is that step 2 doesn't depend on the stream elements. So like if you recall, like the step, I have a mouse, cool. This step is basically independent of the actual stream element. It just does the subsampling based on whether the buffer is full. And I'm gonna basically look at an invariant, and we're gonna show that it's true. And it's basically any element which you encountered already in the stream, the indicator of that element, indicator variable, so like the presence of that algorithm in the buffer, of that element in the buffer, divided by P is actually exactly 1. And that's the key invariant, actually. So like informally, you would say like an element is in the buffer if it was encountered by the algorithm in the stream with probability P. But when you look at that statement, it's actually invalid because P is itself a random variable, right? So that's why you can express it like this. So the expectation of the indicator variable divided by P is equal to 1. And we're going to look at how to show basically that invariant. And so basically, let's say the algorithm already encountered that element. So like we can assume it's true for some state M, which the algorithm encountered, that it's true. And then we want to basically show by induction that it's also true for the next step. And I'm going to just go with this step 2 as an example to show like how to basically establish that the invariant is preserved. So we're going to have to basically get from here to here, right? Like when we are basically applying the step 2 of the algorithm, and we want to show that this is still true. And so I'm gonna, this is just abbreviation for it, but yeah, let's have the term here. And then what I'm gonna do is basically expand step 2. And so what the algorithm does, let's recall, if the buffer is full, then it does the subsampling operation, which then leads to an integral here. And otherwise, it just keeps the element, so like you can actually preserve the expectation from before. And this is basically integration over the possible states when you do the subsampling. And so what you can do here is like extract that P1/2, right? So let's do that, okay? Then you can actually compute it. So like basically what's the probability that an element is in the subsampled set? And it's basically 0 if it's not in G either at all, Otherwise, it's basically 1/2, because we were always independently choosing each element with probability 1/2. So you can compute that. And then you can kind of cancel that out. And the cool part is the if and then case are actually the same. So you can ignore that. And then the cool part is that's actually our assumption. So yeah, works very well. And so that's that's something where you can derive from that the expected count of distinct elements is expected result is the count of distinct elements, right? But that's actually not that interesting. So what we want is we want to establish concentration. Okay. So basically, you want to show that the result of the algorithm is actually concentrated around the expectation. So like basically, like it would be bad if we were in this situation before, but you want to be in the situation on the right-hand side where the probability of deviating too much from the expectation is small. And so what we discovered, and that's kind of like part of the new technique, is you can actually do our recursive inductive proof, generalize it to more complex expressions. So like, for example, like before we didn't have this function h, right? Like we just showed that this is equal to 1. But you can actually show with the same proof, basically, with slight generalizations, that it's true even if you use a function h. And you can even do more. You can actually use like products of the subsets of the stream elements, and you can still show that this inequality is true. And the last part, you can actually show your approximation guarantee basically with that. So you can recursively basically establish that invariant, and then from that, you get that your algorithm is concentrated. And that is basically standard Chernoff bounds, how you do that. Like it's nothing new. And I have to kind of caveat all of that with, you have to look into the paper because like I'm skipping a lot of details. So like, as I said, like the observations are like the algorithm is like much shorter. And the technique, so I've been really looking into a lot of verifications of randomized algorithms, and I couldn't find any case where something like this was used to show concentration for a randomized algorithm. And the cool part is the new proof is actually opens up the design space of the algorithm. So like it's possible to generalize the algorithm in slight ways. And that's how we came up with our new variant of the algorithm, which is unbiased. So I'm actually running out of time, so I'm gonna just mention that very shortly. But basically, like instead of choosing each element independently, randomly removing, you can actually remove a fixed count of elements, and you can still make that algorithm work. And that only works with our new proof technique. Like you couldn't generalize the old proof to verify, to give that new result. Okay, I'm gonna skip all of that. But yeah, like basically, we verified the CVM algorithm. We developed a new technique for the verification of randomized algorithms, and we developed actually a new variant of the algorithm, which is unbiased. And I'm gonna, you have to read the paper when you want to look into negative association. And thanks a lot.